Okay, so uh, before going start the session, I will just give the introduction about Smartgaon. So Smartgaon is a non-government organization, and it is a technical partner of RICHA, and working with basically Smartgaon is working on infrastructure support in rural areas and skill development since last 6 years. And RICHA is a NGO working since last 25 years in area of skill development, counseling and rehab, uh, and counseling for youth, and women empowerment, women empowerment, uh, and under skill development program. RICHA is the implementation partner of IBM CSR project named IBM SkillsBuild in India. So today, under the IBM SkillsBuild program, we are going to organize the master classes for all the partner colleges with IT experts on the topic of career opportunities and scope in semiconductor industries. And today's expert is Mr. Shanker Sharma Ji, who did VTech, ITI Roorkee, and have more 18 years of experience in IT industries and did experience on semiconductor field. He is working in world leading semiconductor company Qualcomm Inc. California, US. So I am inviting to Hari sir to come on and share his experience and his knowledge with us. So please, Hari sir.
Yeah, thank you, Rahul. So yeah, hello everyone. As Rahul mentioned, my name is Hari Shanker Sharma. Yeah, I did my BTech from IIT Roorkee, and then I did masters, and after that I am working in semiconductor industry for last 18 years, and I want to share my experience and the career opportunities available in semiconductor industry. So let me begin with my presentation. Please do confirm me if you are able to see my screen. 1 second, let me share the screen. Can you guys see my screen?
Yes, sir.
Okay. Okay, so yeah, so this is the topic for today: career opportunities and scope in semiconductor industry. So this is a little bit of disclaimer that the lot of content I took it from, I mean, it's publicly available, and I'm using that information only for the learning purpose for non-profit organization. So agenda for today is introduction about the semiconductor, brief on evolution of semiconductor technology, where we stand today, chip design, and I work in digital design, so I will be talking about mostly, I'll be touching upon only the digital design part. So that's where I will be covering the chip design, flow and scope, the complete, basically how the overall chip design happens, exploring the career and summary. So introduction. So here I'm going to briefly touch upon the evolution of semiconductor technology, explore its scope and impact all around. So basically what here I'm going to cover that how the semiconductor technology has been evolved in last couple of decades, and what is its scope and the overall impact. Explore the different steps involved in digital chip design flow, the challenges and opportunities. I'll be touching upon the different steps, like how the digital if you have to design a digital chip, so what are the steps comes into the picture, the challenges and the opportunities. We'll also focus on how the learning done in our colleges can be capitalized when we explore the career into this field. So I will also try to emphasize that whatever we are learning in our colleges during the BTech, like digital design courses, analog design, and the microprocessor design, the basic digital design courses which we study in our colleges, how much importance those courses carry. And so we have to, so I will be focusing on that, and we'll see that later. And then finally, I'll try to summarize all these points. So let's touch upon the evolution of semiconductor technology. So most of the guys might be aware that process node reduction, like from 50 micrometer to 3 nanometer. So it basically started, I think, from 90. If I'm not wrong, then it's like from 80s or 70s. The first node, the transistor, the node size was 50 micrometer, and we stand today to 3 nanometer. You can see how much, and this node size basically reduction means the transistor size is going smaller and smaller. If transistor size is going smaller and smaller, that means we can put large number of gates on our chip. It basically reduces the size, the area, and improves the performance, improves the power requirement. Like it basically consumes less power. So that's the benefit of going to lower nodes. And supply voltage from 12 volt to 1.2 volt. Earlier, like they were using 12 volt supply. Now they went to 1.2 volt. I think they are even going lower. I think 0.96 or something. I think that's the voltage right now. The industry is working. And there is a very famous Moore's law that says the number of active transistor will double every year on single chip. So it started from roughly like 2,500 transistor on a chip. Now we have billions of transistors into a single chip today. The sales revenue, 33 billion in 1987 to 439 billions in year 2020, and projected to grow like 680 billions in 2026 and 1 trillion by 2030. So you can see the tremendous growth happening. So I'm touching these aspects to show you guys that how much scope, the challenges, the research and development opportunities, the different segments of fields like are getting into the semiconductor. A lot of companies are coming in, a lot of usage, applications, everything is coming into the falling into the semiconductor domain. So the slide shows that if this much of work is happening, that means a lot of career opportunities are available. You can basically you can join the n number of companies and number of options available. So this basically tries to project you the scope, the amount of growth, the amount of work happening over there. So and if you see no phones to landline to smartphone, you see that a couple of decades, like 2 decades back, we had a landline, then we are now talking about the smartphones. And we had storage in magnetic tape, then we had a CD, then now we went to we are talking about the storage in terms of a terabytes. So earlier, even we had a floppy drive. I think when I was doing engineering in 2002, I was working on, like, I had a floppy, and then the CDs, they were started coming. Now we talk about the storage in terabytes. And I basically studied 8080 microprocessor in my engineering. Now we are talking about the Intel Core i9, which is like 3.5 gigahertz clock frequency. And we started with the 1G to now we are having 5G. I mean, there may be tomorrow 6G, who knows? So that's a growth in the communication, like 1G, 2G, 3G, 4G, 5G, 6G. And then transformation in gaming industry. So you see the kind of games, the video games, the kind of you play, everyone plays on laptops, and gaming consoles are coming, like remarkable growth, and the quality of graphics. And the industrial expansion in consumer electronics, like we used, you guys can think about the television sets like 2 decades back. Now you see the flat screen, LCDs and whatnot is coming. Like our televisions got sleek, and it's a beautiful experience. The crystal clear graphics on the televisions. So this list is endless. You see that the growth is happening in the semiconductor domain. Now, if you see the sales revenue of semiconductor industry, the idea here to show the graph, you don't really have to see the graph, but if you see by year, the amount of sale revenue, the market growth is happening in semiconductor industry is like it's a very consistent, very phenomenal, and continuously growing. So here, if you see different areas, like if you see during 90s, the computing had like that time, a lot of focus was on computers, desktop and laptops. Now, when we reached in 2000s, like a lot of connectivity, like smartphones, iPad, those things started coming. And now once we reached to 2010, like in this decade, we are all talking about the data economy, like big data, cloud computing. So the different segment of time, the different kind of growth happened, and continuously semiconductor domain is continuously exploring the new areas and basically is getting into our life every day. So moving on. Okay, so where we stand today. So if you see, we have internet right now. In today's world, we are saying Internet of Things, industrial automation, autonomous car driving, connecting cars, electric cars, machine learning, artificial intelligence, ultra high speed internet like 5G, security, infotainment, safety, data center. They're all applications are possible because of so much of growth in basically semiconductor domain. So Rahul, you can keep focused that a lot of people are trying to enter, just allow them. I will be focusing on my presentation.
Yes, sir. Yes, sir.
Yeah, and then you can like smart homes, medical industry, consumer electronics like smart TV, smartphones, laptop, iPads, entertainment, gaming industry, AR, VR, like artificial reality, virtual reality, the media. We have mainstream media, we have social media. So I mean, social media, everyone might be aware, like Twitter, Facebook. They're all possible because of the tremendous growth and opportunity came in the through the semiconductor domain. The space exploration. So right now, the final sentence, what I would like to say, that it would not be wrong to say that today's human life is very much surrounded and influenced by the semiconductor technology on almost daily basis. You get up in the morning, you want to have a coffee, you have a very nice coffee maker. I mean, you can see it's basically the very nice, I mean, very sophisticated coffee makers are. You go and make breakfast like toasters, you go to microwave oven, a lot of you can see, and then you go for lunch or you go for like office, like cars and electric bikes, whatnot. If you see everything, you go to office, you have laptops, everything is basically coming around the semiconductor. And this is the broad range of end user application. If you see, you have in between, you have the chip, which if you see the smart infrastructure, mobile computing, data centers, and like artificial intelligence, smart homes, medical devices. See, like everything is coming through the through this domain. And this, you can see the growth in different market segments. If you see the smartphone market continuously growing, wired and wireless infrastructures, all the connectivity, you have modems, and you have basically Wi-Fi routers in your home, like wireless, wired infrastructure, automotive continuously. In today's car, if you see the lot of LCD screens, the very nice, if you get inside in today's car, there's so much of things like you have audios, you have videos, everything are so sophisticated. It's all coming from the semiconductor domain. Then you have tablets, you have servers, data center, storage, industrial electronics, and the PC market. The very nice, sleek laptops are coming with with a lot of data storage capacity available. You see that the laptops used to like almost 8 to 9 years back, the 10 years back, the laptop used to be very heavy, and you used to get very small RAM size and the hard disk. Now you see that RAM size is increasing. Your storage, now we are solid state based storage, where once you open the laptop, immediately it's ready to go. So these are all possible because of strong inventions are happening in every day in the semiconductor domain. So okay, so let's move to next. So till now, what I tried to cover, just to give you the glimpse, the amount of money, the amount of work, the amount of R&D happening in semiconductor domain. So next, I will be touching upon the chip design flow and its scope. So I'll be mostly touching upon the digital chip design because I am mostly familiar with, I'm working in this domain, so I know more about this area. And there is one analog design that is also equally very prominent, very powerful, and very strong field. So if anyone is interested, people can study and see the scope in analog design also, and it's going very much hand to hand with digital chip design. So I'll be focusing in the digital chip design flow. So in digital, how the chip design happens. So the very first thing comes from the requirement, like what you really want to do. Let's say if you want to make a calculator. So what is the requirement? What kind of calculator you're looking for? So that's the requirement part. First, you have to define the requirement, what you really want to do. And then after requirement, you do the prototyping. So prototyping, I mean, you basically want to make some kind of functional model, not the real chip. So you want to make a functional model. You want to see how it works, whether it's feasible or not. So that's a prototyping. Then there is a front-end flow. Front-end means there is a language called Verilog that is being used to basically do basically we write a code. It's like the way we write a code using C. So we write a code and then we verify the code. That's called a front-end flow. Then there is a back-end flow. Back-end flow means once the RTL coding, the coding part is done, is being verified, then there is a lot of process which we'll see the details. That something happens, how you convert that overall code into the into different formats so that it can be sent. It can be basically sent to the manufacturing industry to make a physical chip. So that's the backend. A lot of work happens in the backend. Then there is a manufacturing, and then there is a packaging. Then there is after packaging is done, you see the physical chip. Then you do the post silicon validation. So basically, post silicon means when packaging happens, whatever chip comes, we usually call it as a silicon. So post silicon means after you see the physical chip, we also do validation, means we verify whether it is working as expected. So that comes on the post silicon validation. Then there is a system testing and deployment. So once we get a chip, or maybe whatever physical chip is coming, it will be part of some kind of system. So let's say you make a chip for the calculator, but calculator, you have to, it will be a kind of a system. It needs to be put inside the calculator. You should have you have a lot of buttons connected to you. Basically, overall look of the calculator, you can think as a system. So then you test the calculator. You press multiple buttons and see it is coming on the screen. If it is a sensor based, is it actually everything working? That's called a system testing, and then deployment. So deployment has multiple meanings. We'll try to cover that, what deployment means. So let's go step by step. So this is if you see, this is the whole flow. This is the kind of diagram. You have design specification. Specification means, okay, what you really want to do. So that's a specification. What kind of functionality you want. Then you basically do a behavioral description. You try to describe what kind of area will be, how much power it will consume, how much speed it will have. So that calls the behavioral description. Then you try to do a design. That's called RTL description. HDL means hardware design language. So we basically write the code in hardware design language. There is a language called Verilog that is being used to write a program for that. Then we verify that program. That's called a functional verification and testing. And then once the program is working, then basically we go, so till here, till functional verification testing, it is called a front-end flow. Once we enter here the logic synthesis timing verification part, then we enter into the era of backend flow. So from here, there are multiple tools which do all these things. So logic synthesis happens. Then after logic synthesis, we get a get level netlist. I will basically give a little bit of idea on about each steps. After get level netlist, we do logical verification. So logical verification means whatever get level netlist you get, then you go back and run, you do a kind of a run multiple test cases and everything, so that you want to make sure at this step, the behavior is very much same as you had it here at this step. This step, they should have same behavior. Behavior shouldn't change once you do this logic synthesis. After logic synthesis is done, you basically do a floor planning. So idea is, because we want to convert it into some kind of physical design. So we want to make sure. So today's chip has many multiple modules. They have like lot of interconnection. They have memory. You have a processing unit. So how they will fit, how they will sit on the physical space. Like you can think of a house you are constructing. So in a house, where will be your master bedroom, where you will be your kitchen. So how you basically make a floor planning, the physical floor planning, how your house will look like. So that's a similar thing happens here, the floor planning, how you want to manage the different building blocks of your chip design, and they will look like, how they will sit physically, and how their wires and the clock and the different connection will be running through different components. That's called a floor planning and place and routing. Then you have a physical layout. So, and yeah, so yeah, so that's physical layout. Then finally it goes to the manufacturing. So that's an overall flow for chip design. So now let's go to more details. So in chip design, what is the requirement? I mean, how do you define the requirement? So requirement means what kind of functionality you are looking for, how much size you think, because size has lot to do with the how much. If you make a bigger chip, it will consume a lot of power, and maybe there are a lot of applications which are very power sensitive. Like if you design a chip for your mobile phone, you don't want to design a chip which is bigger. First of all, it will occupy the bigger area, and that has something to do with the cost, because the size, as much as bigger size is, it is more costly and it consumes more power, and you don't want your mobile phone to consume your lot of battery. So there are a lot of applications, lot of systems. They are very much power conservative, or power aware. You cannot design a system which is consuming a lot of power. And pretty much everywhere, we don't want to basically make something which is consuming a lot of power, and it's expensive also. So that's why, what is the size, how much power, what are the working conditions? So we have to see whether we are designing for something very hot weather or very cold weather, or we want to design something which is running very longer, like something you want to install some kind of sensor in a very remote location, and that place is not very easily accessible. So what kind of working condition? So you'll be designing the system in such a way so that if it cannot be accessed every day, that means that should run on very minimal power for longer days. So those are like a working condition. And then performance, like what is the performance like, whether it should be fast, slow. So comes under the performance. And then marketing requirements. Let's say, how many customers are there? Are there a lot of demand? There is something very unique product you are designing. So that's called a marketing requirement. And what is the future of the product? And what are the usage applications? And how much time it will take to make it? So these things mostly come in as a part of the requirement. So if you are going to design a system or chip something, you need to study all those things. And then prototyping, basically, once you have the requirement, then basically you have to see, you have to do a modeling. You have to design that in a C-based or some kind of model, and as a proof of concept, that whether this kind of thing is actually going to work, and whatever you are thinking, is it actually possible. So not everything what I mentioned here may be possible using the modeling, like a power and working condition. You cannot really test much using the C-based modeling, but at least you'll be able to see the functional modeling part, the functional part, whether it is working the way you expect. Then there are a lot of places, in a lot of cases, MATLAB is also being used for modeling purpose, like in DSP. In digital signal processing cases, there are a lot of filter designing and all those happens using the MATLAB. And okay, so now next part is, once your requirement is done, the next part comes how you architect that particular chip. I mean, how you basically how are you going to realize that? What are what are smaller components you need to make the chip a reality? So the first comes the specification. Based on the requirement, you have to explore the technical aspects of a design. Like technical aspect means what is the size of node. Size of the node means like the transistor size, like we discussed about the, like on what technology you are going to put this design, like it is going to be the 3 nanometer design, or it's a 4 nanometer or 5 nanometer, and the lot of things, they also being driven by the cost, the money, how much, what kind of technology and what kind of architecture you're going to design. That is also very economical. It shouldn't be very expensive that you design something or you're not able to, and a company is not able to make money. So that's these are a lot of things are basically related, connected with your money. The overall the financing side or the economy or economic side, they're driven by the economics. And then like library cells. So size of the node basically decides what technology you are working. Library cells basically, the lot of EDA vendors like Synopsys or Mentor Graphics or Cadence, they provide library cells for a lot of your components like memories or adders or basically FIFOs. There are a lot of library cells are already available to ready to use. That's like adder, or maybe the AND or NOR gates. A lot of library cells are available for those kind of basic gates. And then you need to define the power constraint, like how much power, max power it is going to consume, and the clock speed. What is the clock speed you are going to design? Then they're basic, they're not all the parameters, but I'm just trying to emphasize a couple of points so that you guys can have idea when we actually go for the specification. How do we, what do we call as specification? What can be the possible component to start with? So that's like comes part of the specification. And once you have a broader specification, broader idea that this is these are the components you're going to use. The next thing comes the architecture part. So in architecture, you basically have to work on multiple components, like how are you going to design that particular chip? Basically, you have to create a lot of multiple sub blocks. Let's say how many FIFOs you may need, how much, what is the memory you are going to need, and what kind of buses. Buses mean the connections which do a data transfer. What kind of bus you need? So let's take an example. Let's say you are Intel is working on, let's say, some new processor. So when they're working on a processor, so they have to define like what is the size of L1, what is the L1 memory or L2 memory, or the North Bridge North Bridge unit. What is the speed they're looking for? What is the speed they're looking for on South Bridge unit? And the PCI bus or the SATA or USB, what the speed and all those components they're looking for. So they basically, those are a lot of things they decide, and what kind of DMAs you need, what are the FIFOs you need, how many FIFOs you need, and each FIFO, how much depth for different FIFOs you need. So those are things you basically decide, like sub-block diagrams, connection, the data flow, what kind of interface you need between different components, and the required bandwidth, the pipeline design, whether pipeline in the sense like how much things you can put in under parallel processing, like you want to have multiple parallel designs so that you can process a lot of data in parallel to meet your bandwidth requirements. So those like pipeline designing. Then once you have some rough diagram or idea, then you also have to work on the how much your overall design is going to take the overall area. So the rough estimate, the rough area estimate, you also need to have it. Then memory requirement. What is the memory requirement? How much memory you need? Whether your design needs a memory or it does not need a memory. Then design partition based on the bandwidth and timing perspective. Like you have to put like either parallel pipelines, or you have to decide the multiple stages. Let's say when you send a data, you are seeing output after 1 clock. Like, are you seeing the what is the latency? Like the data is coming right on the 2nd clock or 1st clock or after 10 clock or 20 clocks. So those are like latencies, bandwidth, everything you need to decide. How many clock crossing domains you need, the FIFO requirements. So these are a couple of things you basically work upon when you work on the architecture. These things are very necessary. And by showing these things, I'm trying to show you guys that the kind of work, the kind of work, I mean, the intensity of work, the depth of work, and the complexity of work is involved. There's a tremendous amount of work goes in here. And when there is a tremendous amount of work, the tremendous amount of money and the market, the requirement, the tremendous amount of opportunities are also there. So these overall things, and they need a very, very deep technical knowledge. So like, I mean, if you really, anyone is really looking for a career in all those fields, then you really need to come up with like a strong knowledge in your digital design aspect. So these things will show you that the kind of requirements and the level of knowledge you need to have to work with any of these companies which are working in these domains. So we see the very lot of important point, like discussions on the lot of discussion happens, like sometimes discussion goes on for weeks, or maybe like you can assume like there may be in a group there may be 10, 20, 100 or 200 people, and they discuss for weeks to come up with the the proper architecture, the kind of I mean the overall I mean final shape of a design they're looking for. Each and every point is being discussed to the very, very precise accuracy. They go with the, I mean, they go to very extent. They decide on each and everything to very, very, like you can say 100% accuracy. They don't go with any kind of margin. The very, very, very small margin they go with. And they put a lot of amount of discussion, the clocking, the reset implementation, the overall, how your clock tree will follow, the reset will follow, and then kind of a low power optimization. And the lot of focus is happening on the low power design. Like if you have a multiple components in a design, what kind of component you can switch off in between when that is not needed, while you basically your design is running, or maybe your design is being, your chip is working. Let's say there are two parts, A and B. At some point, A is not needed, so you can shut it off on the fly. So those kind of design, they go right. Those kind of planning happens right in the beginning. So these are the this is how anyone come up. I mean, the companies, they basically decide upon the architecture part. Then once your architecture is done, then you basically go for the implementation. That's called RTL implementation. RTL means register transistor logic. I think register transfer logic. This is RTL register transfer logic. Implementation. So that's where comes when you have your requirement is done, your architecture is decided, and then they decide upon the resources. Okay, block A will be done by the person X, block B will be done by the person B, person A, Y, and like that. I mean, resource assignment happens, and then the whoever has got that particular block or sub block or system, they basically start working on the coding part. So here for the coding, basically the language is being used here is a Verilog and VSDL. The more prominently right now is the Verilog. I guess in some European countries they might be still using the VSDL, But most of the part, I think 90% cases, the Verilog is the language, is the programming language that is being used to write the RTL code. So here, if you focus on this point, all the concepts of digital logic design are very much used while doing RTL coding, for example. And these are the digital logic design concept which you guys during your BTech or masters, you must have read these concepts. So please pay attention to those concepts. They are very basic and they are the most fundamental points. Everyone should be very much thorough with those concepts, like what is FSM, what are the basic gates, how they are being designed, the behavioral logic, the when you write a what is the definition of behavioral logic, what is the definition of combinatorial logic, and the truth table, the Carnot map, the Boolean algebra. These are all concepts are being taught in every undergraduate in electronics or electrical engineering, I guess even the computer science. So these are very basic concepts and they are basic fundamental blocks if you are interested to pursue the career in the semiconductor domain. So this one should definitely be very thorough with these concepts if you are planning your career in RTL design or front-end design and verification. Like what is the flip-flop, what is the latch, mux, demux, decoder, adder, multiplier, and binary number system, hexadecimal, octadecimal, and their conversion to each other. Clock dividers, multiplier, twos and ones complements, synchronous and asynchronous designs, pipeline designs. These are basic fundamentals. You should be very thorough with these concepts because mostly when you go for interview and all, these are, if you are going for a fresh, if you're a fresh college grad and you are applying for a companies, they will be looking for these concepts. You should be very thorough with these concepts. And then when RTL implementation happens, obviously you need to know these concept, and because these will be used when you write your code. You will have to keep these things in your mind, because if you don't know how you design, how you write a combinatorial logic, how you write a behavioral logic, you really cannot write a code. If you don't know how to design an FSM, then you cannot write a code, because FSM becomes FSM is like a machine. Once this happens, then this will happen. This happens, then this will happen. Very complex FSMs are being designed. So you need to have that idea how to design an FSM. So these are concepts are being used, and the number systems, obviously you need a lot. And then low power design, like on the fly, some blocks, how to shut off the block, how to enable the block when block is power off, when block is power on. So those are called low power designs, power aware design. Mostly they're known as power aware designs. So these are concepts comes into the picture when a designer sits and designs, basically write a design. Then, so these are the first few things are very fundamental concept one should be aware. And then next thing comes let's say you are being asked to work on USB. And if you don't know how the USB protocol is, then obviously you cannot design a USB. Then the next thing comes, you need to basically, let's say if you are new, obviously you will learn while you work. So you'll be basically going through how the basically the protocols you need to read. You have to go through the protocols. You have to understand. You have to learn about the architectures. You have to learn about the protocols. Like if you are working in a micro company like Intel and in their processor group, then obviously you have to read the processor concepts, the memories, and all the coherencies and all the caches. You need to learn about those protocols. So that's another step. First, you have to be thorough with the fundamentals, and then on top of it, you basically have to read up about the protocols. So let's say you are working in networking company, you have to read the networking concept basically, or these are required. First of all, you'll be working on the smaller or bigger blocks, and then on top of it, you also have to understand overall how the overall system is working. like communication. If you're working in like in companies which are working on communications, like they are designing a Wi-Fi routers or maybe the mobile modem systems, so you need to aware of communications. We're working on kind of a places where it needs a digital signal processing. You need to be aware of on the, you need to read up about the DSP concepts. And if you're working in a graphics company like AMD or Intel or Nvidia, then you need to be very thorough with the graphics related concepts. If you're working in a company which works on memories, then you need to read about the DDRs and their protocols and their those things, the PCIe or SATA or ESP. So they have their own protocol, they have their own concept. So you need to read about those concepts. So this is the implementation part. After once implementation happens, the lesson, so on the front end there are two parts. One is the design part, one is the verification part. So designer designs the basically makes the design, work on designing the particular module or sub module. Then there is a verification engineer, he basically works on the verification part, and this verification part has lot of career opportunities, because these days if you see, the lot of very complex designs are coming in every day, complexity is increasing. So the role of verification is very prominent, and there are a lot of opportunities in the verification domain. So if someone is interested in this domain, there are a lot of options, there are a lot of opening, there are a lot of work is in this domain. So my most of the career experience is into the verification. So yeah, that's my area of expertise. So I am more thorough with the RTL and the design and verification part. So here in verification, what happens, you have to design your which we call it as a verification environment, which we call as a test bench, basically an environment to test the design. So this is like you have to, and this also consumes a lot of energy even in the planning stage. How are you going to design, how are you, your test bench or this environment, so that you can test your block or sub block or design in a better way, so that it doesn't have it does not, after you are done with the verification, it should not have any kind of bugs or flaw. So that comes part of planning and in implementation. And there are multiple and this test bench can be done, this implementation of this verification environment can be done using the system verilog. So system verilog is a language which is basically a superset of Verilog. So system Verilog has a Verilog, and plus it has a lot more concept. It's very close to, if you read about it, it's very close to C++. It has a concept of all the OOPS concept, like object-oriented programming. It has a lot of concepts of all the inheritance and polymorphism. So those concepts, the system Verilog language carries all the concepts. And then based on the system Verilog, there are a lot of verification environment has been created, like methodologies have been devised, which name is like a UVM is like a very recent verification methodology has been evolved. Its name is Universal Verification Methodology. So that's UVM. Then there is a OVM is being, it's basically a proprietary of Cadence. And then VMM is being designed by the Synopsys. But UVM is very latest. It is being accepted by all the CAD companies like Synopsys and Cadence and Mentor Graphics, and it is pretty much being widely used across the industry. And then how basically this test bench architecture happens. So here also you have to list down all the features and very detailed planning. How are you going to test the overall your design? So the lot of detailed planning goes here, and a lot of a lot of tests you have to create. This, first of all, you have to design your environment, then you have to create the test. So and then once you run those tests on your design, the lot of bugs, the lot of flaw you find, you work with your design to verify, to make sure the bugs or flaws are being fixed by the design. Then you have to get your all tests clean, and then you have to basically you have to design a test to measure the throughput, because like I mentioned before, the performance, the latency, the throughput is very important criteria. So you have to test the throughput, make sure that, okay, whatever throughput has been expected by the design, let's say something needs to work at 1 gigabits per second, is it actually working on 1 gigabits per second? So those things comes through the throughput and latency. Then a lot of other activity comes into the picture. So here in this slide, the one thing I want to point you guys out, there's so much of work happens. The work is happens to be very complex. So then a lot of requirement also comes, a lot of work opportunity, the career opportunity also opens up. So this part has a lot of, even though this lists only a couple of points, but behind the point, pretty much everything, the work goes for like months. It's not a 1 week or 2 week of effort. It's sometimes work goes for like 3 months, 4 months, 5 months, 6 months, even to a year. So that much amount of work happens in this verification part. There's so many details are behind these kind of lines. If you read one line, any line, let's say if you pick up this kind of debug method, tools have improved significantly to provide ease in debugging and finding bugs. That means that a lot of work is happening on the tool company. They are providing, they are working day and night, improving their tools to debug, to help in debugging the verification engineers, so that they can debug easily and find the bugs. They're working because the designs are becoming so complex, so debugging becomes harder. So they are working to provide better tools. We are working, the verification engineers, to debug the design as easy as possible. Even though things are very complex, these tools sometimes help to help in debugging. So these are a lot of work happens. So these are different improvements are also happening. So improvements are also happening on the EDA company side. They are providing better and better tools like Synopsys, Metagraphics, and Cadence. They are working, they are continuously improving their tools to help the designing part, help in verification part. And so a lot of work is happening in this area. Then there is a new, I think it started from last decade or so. Since designs are becoming very complex, so you cannot achieve everything through this verification part. So they're emulation platforms. They're like a new way of basically running a design much longer. So the emulation platform, they basically run your design as if your real chip is running. So real chip runs very fast. So emulation platform also runs things very fast. So something, because in verification, you cannot run something long enough because it has certain limitation. You can run a test maybe for 7 hours or 8 hours. So that's the max, or 10 hours you can run. But emulation platform can actually run the same test, which is running on your verification platform for like 8 hours. This emulation platform can actually run the same test in 2 minutes. So you can actually, using this platform, you can run things much longer, so that you will be able to find any flaw or something. Let's say something you run for, let's say 2 hours, maybe something goes wrong after 1.5 hours. How would you know? So that's where the emulation platform comes into the picture. They basically help to find some kind of bugs in silicon or chip much earlier. So this is another area of opportunity has been opened up, where a lot of employment is coming in this area also. So this is the part. So till here it was all front end, like designing and the verification part. Then we enter into the backend part. Once the designing part is over, it has been verified. Let's say you designed a calculator. So designer has designed basically written a code to work as a calculator. You as a verification engineer have verified, oh, this calculator, this code is working and actually acting like a calculator. For example, let's say you say, oh, 2 plus 2. If it is giving 4, I'm giving a very simple example. So let's say you design an adder. So adder means what? You give 2 inputs and it should give output. So designer basically designs a adder. Okay, you give 2 input, is giving the output. Verification guy, what it thinks, okay, what kind of addition this adder is doing. So you give 2 input and what is the expected output, whether it is coming or not. So that means the adder is working. Now adder has to be basically go to the backend, it has to be converted into the basic gates. Basic gate is a NAND gate. So it has to, using the backend flow, your RTL, the language, the very long language, it needs to be converted into the structural language, which is like a structural form. Like it has to be converted into the basic gates. Like basic gate is a NAND gate. So everything, the whole your RTL code written in a very long needs to be converted into the form of basic gates. Like every adder, subtractor, mux, FSM, or everything needs to be written in the form of gates. So that's a part of the backend. So here, if you see, and this backend part, the first part is basically, so these are the steps like synthesis. When you do synthesis means it's a tool. So that basically takes your RTL design as an input and it generates the file converted into the basic gates. So that's part of synthesis. And then place and routing. Place and routing basically a placing of components into a physical space where who will go where the particular particular block will sit, how the routing will happen, how the wires will flow. So that's a place and routing. The parasitic extraction is basically it's a RC extraction. What is the because these wires and everything, they have a resistance, they have a capacitance. So those extractions also play a very important part. Then a static timing analysis happens. Then post layout verification happens. So if you see the synthesis, what is the synthesis? Synthesis means RTL is converted into the get level netlist using standard cell libraries and based on the defined constraints like timing, area, max transition, and fan out. So there's so many things happen. So these are kind of inputs are being given to the and the tool name is Synopsys DC. So that guy basically takes your RTL file as an input and basically converts into the basic NAND gates. So all your NOT gate, OR gate, and all those things, they're all everything based on the NAND gates. So all the adders, subtractor, mux, and demux, everything gets converted into form of the basic gates. And then after you convert into you get the get netlist, the logical equivalence check is performed to ascertain that functional equivalence between RTL and get netlist before moving to place and route. So once you have the get netlist, we as a verification engineers run the same amount of test cases which we were running before on the actual RTL design to make sure that after conversion, after you got the get netlist, this also works in the same way as it was as the your RTL written in a very long code work. So that's another work area of work. A lot of work happens in this synthesis part. A lot of people are working in this domain. After synthesis is done, then you basically do a place and route. In this step, what you do basically, you do a placements because your chip has multiple components where your memory is going to set, where your adder is going to set, where your DMA is going to set, and how your reset and clock basically will be going to every block where your PLL is going to sit. So everything is being comes here, the placement part. So it basically involves placing all macros and cells into certain and predefined spaces. And the engineers who are working in this domain, based on your domain knowledge, you can lot of tool also helps a lot, but with your prior work experience, you can actually design, you can do a place and routing in a much better way as compared to the fresh engineers or something. So that's where a lot of experience comes into the picture. You'll be able to do a place and routing faster because you have worked on it, you know how things can be placed. So a lot of work happens in this area. Then clock tree synthesis also happens. So basically clock tree synthesis means, okay, how your design is going to from main clock, how are you basically creating a tree and sending basically sending a clock to each and every component, so that if let's say you are sending there is a main clock, and then through the tree you are sending a clock to the very last component which is sitting very far on the other side of the side where opposite your main clock. So how you synthesize, how you send that, create a clock tree so that that block also works in a very much synchronous way at the rest of the design. So these are all part of the clock tree synthesis. The transition time, the clock skew, everything basically should be within your defined limit. They should not basically violate any kind of a clock skew or maximum transition time, the capacitance or setup and hold time. So there shouldn't be any violation. So in this is also a very specialized area. So if someone is interested, like a lot of work opportunities in this domain, and then the routing also, how you connect the different wires, how you run your bus. Somewhere some module needs a 4-bit bus, some module needs 16-bit bus. So those kind of routing also, and there's sometimes very standard uh, buses are available. So those like HB bus or APB and those kind of buses can be used, are being used, I mean, depending upon the requirement, AXI bus. So those are also how you place different blocks, how you connect them. These are all comes as a part of the routing. And then you do a parasitic extraction. In this case, basically you using the tool, you basically create accurate RC model. Basically, you try to analyze the IR drop, and this IR drop basically helps you to measure the power consumption and all those things. That's where the lot of work happens in to extract this the values to know, okay, uh, how much power consumption will happen when you are running with the peak load or the minimum load. So overall, the power consumption, that's basically the overall idea of a parasitic extraction. Then static timing analysis, also you basically try to uh, measure the static timing. And basically the idea is your design, the way you do a placing and routing, you should not end up in kind of a violating any kind of the requirement of setup and hold times. Otherwise, your design will not work, and it's kind of, I think, there is a if a setup or hold time is violating, you will not see the correct data. I mean, being sampled, there will be a problem. Your design will not work as expected. And then there are multiple timing domains are being used, like when you are working in a like a typical timing. TT means a typical timing, FF means fast timing. So there are different kind of a different timing mode the design is being run. So that, because when you it depends upon the, sometimes depend upon the usage. Something is being in device is being in very hot weather or cold weather, so those have some impact on the characteristic, physical characteristic of a metal. So that's where we try to run these different timing corners, and so that even though some physical variation happens, these timing, different timing corners don't end up violating any kind of a behavior. So that's why we try to, I mean, the engineers try to run the design in different timing domains. So that's another area of work happens in the on the backend side. Then once this whole thing, placing, routing, connection, everything is being done, then these are some final checks are being performed, like layout versus schematic. Like, what is the final layout has come, whether it is actually matching with your with your schematic or netlist. I mean, when you started netlist and when you came finally, is that matching? And then design rule checks, like process of checking the geometry in GDS file follows the rules given by the foundry, because your manufacturing company, they also have certain rules. So this also has to follow that rule. Then logical equivalence check. So whatever you have a final net list after place, route, and everything, it is not any different than your pre layout. The behavior and the behavior, whatever you had before, your functional behavior should not change. It should stay. It doesn't matter how you place and route and connections, whatever you do, behavior should stay intact. Throughput should meet, timing should meet, area should meet, power should meet. So those are things happens. So there are a lot of work happens in this, like sometimes these designs run for multiple days, like 6 days, 7 days, 8 days, because designs are very huge. They run for multiple days. These checks run for multiple days to to get the results. And then finally, once you have everything, then this file goes to the foundry for manufacturing. Now this is the, so backend ends here, then it goes to the fabrication packaging. So there are a lot of companies like TSMC, Samsung, or Intel. They have foundries, and they basically do the manufacturing. So manufacturing is also a very complex process requiring hundreds of precisely controlled steps that result in pattern layer of various material built one on top of another. So when the chip fabrication happens, the multiple layers there's a metal layer called base layer, and then some more layers, like multiple layers of designing happens these days. So there are very precise operations. So you can read more about either through Google or something. You can read a lot on the internet, a lot the basic the technical details, the more technical details about the fabrication packaging. And there are a lot of these companies are expanding their operations, like foundries are coming up even in India. So the lot of work opportunities is possible in these companies. I think the couple of announcements I have seen that some foundries are coming to the India. So this is also one of the very interesting field where this chip manufacturing is happening. So after manufacturing happens, there are a lot of uh, tests happen after manufacturing, like like they're being one the whole disk kind of thing, which is called a wafer. On that wafer, you based on the smaller the node size, smaller will be the chip, and those many chips can be manufactured on a single wafer. So if you're for example, let's say you have a 7 nanometer node size, and if you are able to design, let's say, 20 chips on that wafer, if you go to the from 7 nanometer to 3 nanometer, your node size is decreasing, means your transistor size will go down. That means your chip size will shrink. So instead of 20 chips, maybe you'll be able to manufacture like 30 chips. And the manufacturing, these companies, they charge based on the wafer. So let's say one wafer, they charge $20. So within $20, with the 7 nanometer node size, you were able to manufacture 20 chips. If you go to node 3 nanometer, so your chip size will be shrink. So maybe within that same wafer size, you'll be able to manufacture 30 chips. So for if they're charging $20 the same, then you can see you're getting more number of chips manufactured within the same amount. That's how this economy works. When you go for smaller nodes, in the same wafer size, you can basically manufacture more chips. So your chip manufacturing cost goes down. So that's the benefit of going smaller node size. At the same time, smaller the node size, smaller the power consumption, so it consumes less power, and also some static power in those things play more role. So that it's not very straightforward formula, but smaller the node size, definitely it reduces the chip manufacturing cost. That's why people keep going down to smaller and smaller node size. So after your chip has been manufactured, is being packaged, then it comes back to the lab again. Let's say Intel has manufactured a chip. Once it is manufactured, packaged, it comes back to the lab again. And in lab again, the post-silicon validation related activities are done. So same kind of, a lot of tests are being performed, and they are being actually being fit into the actual PCB board. They run with the actual firmware, actual software, in actual system environment. They are being tested one more time. All your functional cases are being run, all different kind of parameters like temperature and the clock variation. The lot of different environment related conditions are also being tested. Like you run much longer, you run straight for like 2 days, 3 days, you keep running something. And so those kind of tests are being done to check their reliability. And so those kind of lot of test happens, bring up test happens on the post silicon. And there are a lot of tests like automatic test equipment. There are a lot of there are a lot of testers are coming. There are a lot of companies which are designing the testers where you can actually they generate some known patterns, and the output they detect the known patterns, and that's how they are able to test if chip has proper wire connection and all those things. So this is another area where a lot of people like to work in the labs. So if someone has interest to work in this domain, there are a lot of lot of opportunities are in this kind of work. And it's a very technical. It's not that it does not require any knowledge. You need very solid knowledge about the physics of of your because it's all dealing with, you are dealing with the metal, so you need to have some idea about the physics, the temperature effect, and all those. So along with the semiconductor, the basic digital design and all those engineering concept, you need to be aware about the physical aspect of physics about these metals. So that's also very interesting field, and very aggressive work, a lot of demanding work, and people spend days in the labs to bring up the first chip. Let's say the first processor chip is coming back. It takes lot of effort, and to bring up the very first chip, it's like it's not very straightforward. It takes it's a very tedious and very complex work. So that's post silicon validation. And then the next thing is I will so till now I have tried to touch, like, okay, I have tried to show you the growth, the amount of growth happening in the semiconductor industry. Then I have showed you the steps involved to in the chip design. I will be trying to touch upon the exploring the carrier. So like we have seen the design process, like how much I mean, like very lengthy process and very tedious, very complex, and very time consuming, and it has direct impact on the amount of dollar are being spent. So you can think of, like, today a very complex chip can take anywhere up to like up to some 100 to 200 million dollar to even manufacture a single chip. The first chip which goes, the first time it comes from the manufacturing company, it is somewhere the cost is around 50 million to 200 million, depending upon the type of chip is being manufactured. It's very complex, very costly, and very time consuming. So here, that's why, and so many people are getting involved at various steps, so that just to reduce the flaws in the design, because you see the manufacturing cost is very high. And so if chip has a manufacturing bug, then it has to be either addressed by the software or firmware, or sometimes it has to be respin. If you go for respin, you fix a bug, you see the whole lengthy process, again the verification, the backend, all the again synthesis, placing and routing. It's a big process. It takes a lot of effort, and the dedication or the aggressiveness in the resending the chip back to the manufacturing. So it's very time consuming and very kind of serious business, and to go for another release, it's a very expensive. It's not a software where you can patch the release, you can fix overnight software bug and you can release a patch. Here the bug can be very, very costly. So that's why a lot of people get an employment opportunities, and because the chip companies, they want to make sure their chip goes to the manufacturing company with as less as possible the number of bugs. Obviously, being as a human, mistakes can be made, but in this process, chip design process, we try to minimize as much as possible, near zero number of bugs we want to see once chip comes back from the manufacturing. Then here, so these are different domain, like digital chip design, the analog chip design. You might have heard about A to D and D to A converters. They are like huge area of opportunity for in analog chip design. Also, there is FPGA. Then there are system designs. So some people, let's say you might be working a Samsung on Samsung phone. So that's called a system. you might be working in Intel, or you might be working in a Qualcomm, or you might be working in Apple, where you are actually working on some smaller chip. Maybe you are working on DDR, or you're working on a processor, or you might be working on, let's say, graphics chip, or you're working on audio chip or video chip. So that is like a different area. Or some are like system means either you are working on directly on the Apple phone or Samsung phone, or maybe a Dell, which is like basically you're designing a whole laptop. So laptop is a system, a phone is a system, or maybe if you go to the consumer electronics, maybe a oven might be a kind of a embedded system. So that's a system. So you have a system design, and then these are like hardware part. Now you go to the system firmware and software. So there are a lot of requirement to write a firmware and software. They're based on C language. So if someone has a interest to work in a semiconductor company, but they want to be more on the software side, so there is a lot of requirement for writing a firmware or softwares. And then there are a lot of people who maybe they have interest, but they want to be even on the application side, like you want to work in artificial intelligence like AI or ML, like machine learning, or maybe a big data. So you are on the again on the little far side on the software, but still you are very much connected with the semiconductor chip or the system coming to you. And then there is another where like EDA tool companies like a Synopsys, Cadence, or Mentor Graphics. They design tools, softwares, which are being used by the people like us working in a semiconductor industry. Like I'm working in a certain company like Intel, NVIDIA, AMD's. They're like a chip design company. They use a lot of tools designed by the EDA tool companies, and they're pure software. So there also you will be dealing with the semiconductor concept, but you more or less you work on the tools side. So that's another area. So this way you can see that a lot of, it's a very big market, very big demand, a lot of challenging opportunities are there, and it's everywhere, whether it's being research, marketing, engineering, education sector, pretty much everywhere. It's a huge area. Like, and just a little bit about a lot of startups in semiconductor domain. They're mostly in artificial intelligence, machine learning, IoTs, low power, renewable energies, connectivity, medical industry, and a lot of growth in automotive and industrial automation, electronics. And the market like India and China, they're like a big market for semiconductor growth. There's a lot of opportunity in those subcontinent. And there are a lot of, it's not that there are a lot of companies that are working in chip design and system designs. And so so you guys can think like data has become a very, very kind of data is now everything basically. So very valuable asset. So, and this semiconductor, the whole thing, like whether being your smartphone or maybe your storage, memories, everything or it's a cloud, or everything is dealing with the semiconductor company. So we can see it is pretty much semiconductor is everywhere. So that gives a lot of opportunity for the career. Now just a little bit I want to summarize. So like touched upon the overall evolution, the flow of digital chip design, the scope, the challenges. So as an abstract, you can say that this field is very much part of our life and will be there in the future. It's not going to go down as much as we go for like 5G or 6G, or maybe applications like whether it's a medical industry or connecting cars or smartphones or smart homes, industries. This thing will grow. So that's the essence. So you can, I mean, if you have interest and you want to be part of this industry, you can have a very positive impact in the society in your own way, with your own interest. So you can see, you can think about, I just mentioned two examples like Steve Jobs, the co-founder of Apple, or Elon Musk, founder of Tesla. You can think Apple is today everywhere. I mean, if we see today Apple iPhone or iPad or iPod, that's because of Steve Jobs. So you can see how much impact it is having on us every day. And then Elon Musk, the founder of Tesla, you can see that the kind of electric car industry he has revolutionized. I mean, that's amazing. I mean, so that's how, I mean, that's the power of semiconductor industry. That's the power of research. The R&D is being done, or the progress is being made in this field. So it's very interesting, very complex, and very demanding. So it's a lot of scope for career. And these are a couple of, I mean, these are the references I have taken. So you guys can go through it, and yeah. So that's pretty much I had. Yeah. So Rahul, now it is to you.
Yeah, thank you, sir. Thank you very much. Now, students, if you have any question, or teachers, if you have any question or doubts, please put it on the chat box so that we can take it. Yeah, we already have a group, WhatsApp group, which I shared in the chat box. So if you have any question, doubt in later stage, you can put over there also, and we can we will be happy to solve your doubts and questions, right?
Yeah, I just want to add that probably I may have one more session on the, especially touching upon the design and verification, because I'm more familiar with that area. So next week I can have more sessions. If anyone is interested specifically in the front end RTL design and verification, yeah, they can come and join the session. And if anyone, like people are more interested on the backend side, I can have my friend to do more detailed presentation on the backend side. Like he can go in more detail. He can deep dive into every technical aspects of different steps on the backend. So that is also one possibility. The idea is, it's like you need to when you enter or go for an interview or try to pursue a career in this, like definitely it requires a very it's a niche area. It requires a very strong knowledge. And any interview, if you go it, I mean, until unless you don't have a fundamentals clear and strong, it's very difficult to get into the and get the opportunity to work. So fundamentals are very important. You need to have a knowledge of the flows and concepts. You don't really need to know the previous part, like how semiconductor industry is growing. That I just showed you to show the strength and the depth and the requirement in this field. Only thing you need to be focusing upon which is your area of interest, and then you brush up your knowledge and go with a very strong foundation. You don't just venture out with just half knowledge, because that will be probably, that may not help. So you need to have a very strong fundamentals. You should be able to answer pretty much at least 90% of the questions being asked in the interview.
Yes.
Yeah.
So yeah. So if any doubts or questions, student, do you have, please put it on the chat box, or you can also put the questions on WhatsApp group, right? Okay, I think students have not any question right now, and I think they will connect let with us on later stage.
Yeah.
So
yeah, so I'll just give you very brief that the next session I will try to show, will go little bit, we'll try to touch upon the Verilog, very basic, like how the design looks like and how the verification environment looks like. You will find it very interesting. So just if you have interest, just join that one, and then you will know like a very small, very top, I mean, it's a very small part of the view that, okay, how, what it looks like. And then you can see if that has any interest to you guys.
yeah.
Yeah.
So thank you, Hari sir. You give your time to students, and I will also thanks to all the teachers or the faculty members who support us to connect the students. Thank you, everyone. Thank you.
Yeah, and one more thing, like Rahul, you want to announce that this video is going to be on your Smartgaon Facebook or somewhere. So if anyone wants to refer it, they can refer it again.
Yes. Basically, all the recorded session will be available on the Smartgaon YouTube channel. So you can please subscribe the channel and get the videos. Thank you everyone. Thank you, sir.
Yeah. Okay. Thank you, Rahul. Thank you very much.